so far, the only method that we've used to decide whether a set of vectors is linearly dependent or linearly independent is by putting them into the columns of a matrix and augmenting that matrix with a column of zeros. And that's essentially using Theorem 2.5. Now I'm going to show you an alternative approach by putting the vectors into the columns of a matrix. So let's look at an example. These are the three vectors we had from the first example in the linear independence. What we can do, instead of putting these into the columns of a matrix, we can put them into the rows of a matrix. -1, 3, 2, 2, 1, 1, 6, -4, -2. Now in the future, what I'm going to want you to do is this. You're going to use Gaussian elimination, and you're going to find the matrix -1, 3, 2, 0, 7, 5, 0, 0, 0. And you'll notice that this guy here, that's a row of zeros. And so since we have a row of zeros, therefore the rank is 2, which is less than 3 equals the number of rows. Now, you can look at this and say, okay, where did this come from? Did I just pull this out of my butt? No. Here's why this works. So, why it works. And I'll put this as a theorem in a moment. Why it works. So, over here, I'm going to do this going to be very explicit in how I do the Gaussian elimination. So the first thing is I'm going to go here and I'm going to say, okay, let's let row 2 prime, so our new row, be row 2 plus 2 times row 1. So that's old row 2 plus 2 times old row 1. And let's set row 3 prime equal to row 3 plus 6 row 1. I don't know why I'm doing that in blue. So when I do that, I'm going to get -1, 3, 2, 0, 7, 5, 0, 14, 10. Okay, and the first row of my matrix is row 1 prime. The second row here, that's row 2 prime, and this one is row 3 prime. And now I can do row 3 double prime equals row 3 prime minus 2 row 2 prime. And when I do that, I get the matrix -1, 3, 2, 0, 7, 5, 0, 0, 0. So now I'm going to show you why I did all this. Okay. Before I do anything, let me give names to these guys. This will call U, V, and W. So going back to here. So from this row right here, that tells me that I have 0, the 0 vector, that row, is equal to row 3 double prime. So this guy right here, that's row 3 double prime. That's what I call it. I'm naming that row 3 double prime. And from this row operation right here, I know how row 3 double prime is related to the rows of this matrix. So it is equal to row 3 of the the second matrix minus 2 times row 2 of the second matrix, which, okay, now I can use that I have row 2 prime in terms of row 2 and row 1 of the original matrix, and row 3 prime in terms of row 3 and row 1 of the original matrix, to give me row 3 plus 6 row 1 minus 2 times row 2 plus 2 row 1, which is equal, when I expand everything out and collect like terms, to 2 row 1 minus 2 row 2 plus row 3. But row 1, row 2, and row 3 of my original matrix are exactly U, v, and w. So in other words, I've figured out that 2u minus 2v plus w is equal to 0. In other words, u, v, and w are linearly dependent. So where did the rank thing come in? Well, because the rank is less than 3, that means that one of the rows is entirely 0. That's where that rank comes in. And now let's put this as a theorem. Yay! So this is exactly what I've just been saying. So if we have m vectors in Rn, and if we put them into the rows of a matrix, then those vectors are linearly dependent if and only if the rank of that matrix is less than the number of rows of the matrix, is less than the number of our vectors.